Greetings! In this video, we're going to kick off Chapter 4, which is all about transformations. We will define what it means to transform something in the geometric world, and we will perform a specific type of transformation called a translation. Shall we begin? I think we should. Let's begin by defining what it means to transform something in the geometry world. Now, you've probably heard that word transform plenty of times before. It means to change something, and that same definition holds true in the world of geometry. A transformation is a function that moves or changes a figure in some way to produce a new figure. There's different types of transformations. We'll focus on them one at a time. Transformation is just the general term meaning you've changed a figure in some way. The original figure, the one that was there before you changed it, is called the pre-image, and the resulting figure after a transformation has occurred is called the image. So notice the pre-image has that nice prefix pre, which means before. So before any transformations have occurred, we call the figure the pre-image, and then it's been changed, it's been altered in some manner. We call that resulting figure the image. Now, as I said earlier, there are different types of transformations. We're going to focus on just one today called a translation. So let's define what that type of transformation is. A translation moves every point of a figure the same distance in the same direction. We say that a translation maps a figure along a vector. Each point P is mapped to a new point called P prime. And that is what that little apostrophe means in the math world. That little apostrophe is called a prime. And I'll show you what I mean down here with this nice little quadrilateral. I've got a quadrilateral where one vertex has been labeled P. A translation would move that figure in some distance, in some direction, until it lands somewhere new. The new figure looks just like the original, but every point has been moved the same distance in the same direction. And each original point retains a name that looks sort of the same. It uses the same letter, but a prime is attached. And that's how we can designate the difference between the pre-image and the image. The image is always labeled with each point as a prime of the original. So if I were to call this corner here point O, this new location here would be called point O prime. Likewise, if I called this R, hey, this one is R prime, and then let's call this one Q, making this point here Q prime. So the pre-image is labeled with your uppercase letters, just as we've been naming points all trimester long. And the resulting locations, the image, uses the same letters, but each one has a prime attached to it. And that's how you can tell that this one here is the image versus this one here, the pre-image. Now, I snuck a word in here, and that word is vector. In order to translate something, we need a distance and we need a direction. Which way should I move it? How far should I move it? And a vector does a nice job at describing both of those things, how far and which way. So let's define what that term means and see how it can help us with our translations. A vector is a quantity that has both direction and magnitude. And magnitude is just a fancy word for size. A vector is represented in the coordinate plane by an arrow drawn from one point to another. This picture right here shows a vector. You can see it also looks a little bit like another geometric figure that we've worked on in this class, a ray. But this one here is a vector. There's no real indication in the picture as to why it would be a ray versus a vector. The naming will help, and we'll get to that in just a second. So you can see it's in the coordinate plane. It's on that grid. I've got my grid lines in there, and I have a point here and a point here. Point P is what we call the initial point of the vector, initial meaning beginning, and point Q is what we would call the terminal point of the vector, the ending point. There is a direction of this, and that's what the arrow indicates. That vector is pointing in a particular direction. And there is a magnitude of that vector, how long it is, how far it is to get from point P here to point Q here would be your magnitude. Like everything else in the geometry world, we can name this figure. Vectors are named with their initial point listed first and their terminal point listed second, and it gets a nice little fancy symbol above it. It looks a little bit like the symbol that we used for array, but instead of having this sort of, arrow with two arrowy parts to it, it's an arrow with only one arrowy part to it. And that's definitely not the official name, but this is definitely the official symbol for a vector. So this is a vector called PQ, and that's how you would say this out loud. This is called vector PQ. That's its name. Other things that you need to know when it comes to dealing with your vectors. Again, vectors do a nice job of describing how to translate a figure. Vectors need some sort of number associated with them. If I'm going to use a vector to tell me how far to move a figure, I'd like a number associated with that. So every vector has what we call two components, a horizontal component and a vertical component. The horizontal component describes how far did you have to travel horizontally to get from point P to point Q. Well, here the horizontal component of this vector is 3, because to get from point P to point Q, we have to move 3 units to the right. The vertical component of this vector is 2, because to get from point P to point Q, vertically we have to move 2 units up. The horizontal and vertical components are then combined to create what is called component form, a nice compact way to describe the direction your vector is traveling. And component form looks like this. The component form of this vector is written in this form right down here. The horizontal component is written first, the vertical component follows after a comma, and we surround those two numbers in a unique shape of bracket. They are not curved parentheses, but they're more pointy parentheses. Again, not the official name, but a decent enough description. So the component form of your vector has the horizontal component followed by the vertical component separated by a comma, and they are surrounded in these pointy parentheses. Anytime you see parentheses of this shape, that is providing you with the component form of your vector, telling you horizontally 3 units to the right, vertically 2 units up. 2 more examples of naming vectors in component form would be with these 2 vectors right here. This is a vector that starts at point J and ends at point K, so we call it vector JK, and its component form is 3, 4. That's usually how we say it. Travels 3 units to the right and 4 units up. 1, 2, 3, 4. Yeah, 4. Notice this vector here moving to the left. So when I look at its horizontal component, that horizontal component is negative. And that negative means that this vector is traveling to the left instead of to the right. Think about your XY axis from back in your algebraic days. To the left is the negative x direction. That's why this horizontal component is negative. Likewise, if we had a vector that instead of pointing more upwards was pointing downwards, the horizontal and the vertical component rather would be negative. So those positives and negatives associated with your horizontal and vertical axis also travel along with your component form. Let's see what this looks like in an actual example of performing this transformation, specifically a translation. They've told us here that the vertices of a triangle called DEF are located at these points, and this is how you name coordinates. The name of the point followed by its coordinate location in parentheses. Point D is located at -3, -1, and I've gone ahead and plotted all these points. Point E is at -1, 2. Point F is at -1, 3, and they form a triangle, so I played connect the dots and I made it into a triangle. We are asked to translate it, so this triangle is going to move somewhere else using this vector. So let's read this component form in the manner that we just learned. The horizontal component is 4, so that means this triangle will shift to the right 4 units. The vertical component is -1, that means this triangle will shift down 1 unit. The definition of a translation is to move every point the same distance in the same direction. Well, triangles have lots of points. They've got these 3 corners, but they have all the stuff in between. But the easiest thing to do is just take the 3 vertices, those are your angles, and move them according to this vector. So point D needs to move to the right 4, 1, 2, 3, 4, and down 1. I'll put a dot right there and label that point D prime. That's the new location for point D. Let's take E and travel in that same distance, same direction, to the right 1, 2, 3, 4, and then down 1. We will then label this point here E prime. It's like point E version 2, and F 1, 2, 3, 4, down 1. There is point F prime. Let's connect the dots, and I am going to cheat and use my straight line maker. If we were doing this paper and pencil, we'd probably use straight edges, we'd use rulers. So since I'm doing this electronically, I'll use the next best thing. And there we go, a new location for triangle DEF. And you would call this new triangle, triangle D prime, E prime, F prime. Each of those points has a new name with a prime after it. The other thing we need to talk about is that vectors are one way to name how to travel from one location to another, but we can also describe specifically how the X and Y coordinates are changed. So translations can be expressed as a vector, A comma B, horizontal comma vertical, but also using a rule, which has this notation here. And it looks much more complex than it really is. It's like X, Y, arrow, oh my gosh, this is all it's saying. Take the coordinates on your original shape, and the arrow says do this to them to show where they're going to be on the new shape. Take the original X coordinate and add A. Take the original Y coordinate and add B. That's all this is asking you to do. So a vector, as a rule, would look like this. This means shift to the left 5 and up 7. That same translation expressed as a rule looks just like this. Take the original coordinate, and every X coordinate, you should subtract 5 from that. Subtracting 5 from the X coordinate is what's going to move it to the left 5 spaces. And then likewise take the original Y coordinate and add 7. And adding 7 to your Y coordinate is what's going to move it up 7 spaces. To show you with an example here, let's say I have this point, 3 comma negative 2, and I wanted to follow this rule right here. Well, I would take the X coordinate, which is 3, and subtract 5 from it. I would take the Y coordinate, which is negative 2, and add 7 to it. That tells me the new location for A. We would call that A prime. 3 minus 5 is negative 2, and negative 2 plus 7 is 5. So the original point A was here, and then it was transformed into this new point, A prime, which is right here. So writing this as a rule looks more complex than it really is. It still means the same thing. Move to the left 5 and up 7, or whichever direction and amount you need to travel. A real quick example to help you see that one more time. Write the vector and the rule for the translation from triangle ABC to triangle A prime, B prime, C prime. So here's triangle ABC, the original, triangle A prime, B prime, C prime, the new one. First, let's figure out how far this shape moved. And I'm just going to pick one of my 2 points and follow where it went. Let's just use point A. Point A started here, and it's moved to point A prime right there. So let's see how far it traveled. It moved to the left 1, 2, 3, 4. So maybe I'll just write that down so I don't forget. Left 4, and then it moved to the up. That's right, I said to the up 1. 1, 2, 3, 4, 1. And all of the other points should have moved the same amount. So as a vector, that would look like this. Left 4 means my horizontal component is negative. Up 1 means my vertical component is positive, and I surround that in these parentheses. So there's your vector's components. And then as a rule, that's the one that looks more complex than it really is, but writing it down can be a little tricky. We first say that the original coordinate xy, so you need to write that down, is transformed into, and then we describe how those coordinates are different. The x coordinate, well, it moved left 4, so all the x coordinates have 4 subtracted from them, comma. The y-coordinate, well, they all moved up 1, so every y-coordinate is 1 bigger than it was before. So this is what that translation would look like if you were asked to write it as a rule, and this is what it would look like if you were asked to write it as the vector. The final piece of this lesson here are 2 vocabulary terms, which are important to utilize because they come into play every once in a while throughout our work here in chapter 4. The first is a rigid motion. A rigid motion is any transformation that preserves length and angle measure. A rigid motion is a transformation that does not change the size or the shape of your figure. The sides of your shape don't get any longer. The angles of that shape don't change. It's not as if a right angle turns into a 60-degree angle. They stay the same. A rigid motion can also be referred to as an isometry. A translation is a type of rigid motion. When you translate a figure, you don't make it any bigger. You don't turn a right triangle into an obtuse triangle. It stays the same shape and the same size. A rigid motion creates pre-images and images that are congruent to each other. So if you happen to be performing a translation and you notice your 2 triangles aren't the same, then you've made a mistake somewhere along the way. Your triangles should always be congruent. And then the final term for us here is a composition of transformations. Composition means you've got more than one of something. A composition is a collection of items. In this case, a composition of transformations means there's more than one transformation occurring at the same time. So maybe I perform a translation following this vector, and then I do another translation following this vector. So I move it one way, and then I move it another way. Performing multiple transformations is what we would call a composition. This video described a lot of information to kick off your translations chapter. We will add more types of transformations as we move through this unit. Today was just one of a couple of different types of ways that we can transform our figures. Hopefully we've transformed your knowledge about this topic. Have a wonderful day, and let me know if you have any questions. We'll talk to you soon. Bye.